All right, this is just a quick PowerPoint review over our there we go, over our Chapter 1 review. It's on linear functions and rate of change. And hopefully this has all been ingrained to you in Integrated 1. I know that was quite a while ago. But we also did a little bit in Integrated 2, and probably not as much as we needed to do. But we did talk a little bit about domain and range and functions. So I'm going to start there. This is just an overview, and this chapter is really for you to read, skim through the sections in Chapter 1. We really don't want to take a whole lot of time on this because it is easy and it is something you should already know for the most part. Just know that a function is a rule or a relation, really, that takes one input, puts it into the function, and it spits out an output, is the easiest way of saying it. And we talked about quadratics last year, and what we put in for x is called the domain, remember? And what we spit out, sorry about that, what we came out with was the range, the output, okay? And the function itself was the quadratic equation, okay? Now, functions we can look at as words, as tables, as graphs, formulas, just all kinds of different things. And if you look in page 2 and 3 in your book, it's pretty interesting. The snowy tree cricket actually can give us an approximate temperature, outdoor temperature, in degree Fahrenheit using this formula right here. Temperature equals 1/4 the chirp rate per minute of the snowy tree cricket plus 40. Now we can write this in function notation like that. This is what we're used to, but we need to get used to this function notation. So let's say we want to make it in tabular form. Well, then we would go, okay, we'd need numbers, right? We put in 0, we'd get 40 for the predicted temperature. Let's say we had, I'm looking for easy numbers here, 20. 1/4 of 20 is 5, so it'd be 45 degrees. Let's say we have 40 chirps per minute. That'd be 50 degrees. Let's say we had 60 chirps per minute. That'd be 55 degrees. And we could fill out the chart, and that would be a function. Well, we could also graph that function very easily, and we can see that this is a linear function right there. So that is another way to model this function, and that's why we call them mathematical models of functions. Okay? Now, I said that word relation before. Relation is just simply you take a set over here and a set over here and you relate them to one another, okay? Usually with a function. Now sometimes the function isn't a function because by definition each function has one element of x, or the domain, that maps to one element of the range, and only one element. Because let's say that we get something that looks like that. Is that a function? Yes, it is. But the minute we get an x that maps to two f of x's or two y's, we don't have a function anymore. Then it's just simply a relation. So one input can only have one output to be a function. But like in this example, this picture, this input has two outputs. So that makes it not a function. Now you're used to seeing that as it relates to graphs, the vertical line test. Well, is this a function? The answer is yes, because each x has one y. But what if I did this? Is that a function? Well, Yes, because each x has one y. Is this a function? No, because this x right here has two y values. Therefore, that relation would not be a function. And that's really 1.1. Now in section 1.2, we get what we call rate of change. Another way of saying that is slope. In integrated 1, you probably didn't use the rate of change. Rate of change is really more geared to application. So we're actually talking about slope, but we're looking at how whatever is changing over time. We call that the rate of change, the average rate of change. So that would be like your acceleration. If you're driving somewhere, you're going to go faster at certain spots or slower at certain spots and so on. So that formula, slope formula is y2 minus y1 over x sub 2 minus x sub 1, correct? That's from integrated 1. Well, this is the same formula, but if we find rate of change, you always use the last point minus the first point, always, meaning the right one on the right on a graph minus the one on the left on a graph. So if we look at this graph at the bottom, if I look at these 2 points, the average rate of change is negative. How about from these 2 points? Positive, right? How about from these 2 points? Negative. How about from these 2 points? Positive. But if I look at these 2 points, what's the average rate of change? There is none, is there? It's 0. So we can look at the average rate of change between any 2 points. So let's say we have a function like this. This is called a cubic because it has a 3 in it. Not sure what the cubic looks like. I know it's a chair function, and you'll learn that this year. But let's look at the rate of change. So the average rate of change is going to be the slope. And that is going to be, we're going to have to put in the points because we need to find our y value. Because this is how we find our y value. And anytime we substitute a number in, make sure we put parentheses around it. Because this negative means the opposite of 1 cubed. So we get negative 1 plus 3, which is 5. And then f of 0, well, that's simple. Negative 0 cubed plus 3 times 0 squared plus 3, that's simply 3. So if we're going to find the rate of change, we are going to find the change in y from this point, which is 5, minus 0, which is 3, all over 1 minus 0, which is 2 over 1, which is 2. So between 0 and 1, our equation has a slope of 2. So it's going up from 0 to 1, something like that, with a slope of 2. 2 over 1, rise over run. Okay, we already know f of 1 was 5. So what's f of 3? Well, negative 3 cubed plus 3 squared plus 3 is negative 27 plus 27 plus 3, which is 3. So that's going to be 5 minus 3. Hey, it's going to be the same thing, isn't it? Nope. Because we're going to have 2 over 2, which is only 1. So it's going to start leveling off. I hope I did that right. 3 minus 1 is 2. F of 1 is 5, and f of 3 is 3, so that's correct. So it's going to start leveling off from 1 to 3. So the slope's only going to be 1 over, or 1, I should say. So it's going to be not as steep from 0 to 1. It's steeper than it is from 1 to 3. Okay? So that's how we calculate the average rate of change, which leads us into a line. Now, some books will show it this way, guys, and I know you're used to mx plus b, and so am I. So that's how we're going to discuss it. So if you look at P of x and Q of x, can you tell me which one or both or neither is linear? As you can see, each x goes up by 5. So our y value must also go up by a constant in order to be linear. So P of x is, because it goes up by 0.01. But look at Q of x. It goes up by 2 cents, or 0.02, 0.03, 0.08. So this would not be linear. The first one is, the second one is not. Now, just some quick hits from linear functions. Remember, slope-intercept form is y equal mx plus b, where m is the slope and b is the y-intercept. How do you find the slope of this? Well, you must put it in y equal mx plus b form. So if we write this out and say, okay, let's add 7x, because we're going to get 2y by itself. We get 7x plus 8, divide by 2. So y equals 3.5x, I don't like that, 7 halves x plus 4. So what's the slope? 7 halves. Now why do we keep it that way? Because remember, it's rise over run. And if I was to graph this, I would go up 7 and right 2. So we want to try to keep that in fraction form always. Now here's something that a lot of people forget, point-slope form. Point-slope form is probably as friendly as any formula that we can have when it comes to linear, when it comes to lines, linear equations. Given 2 points, if I can use point-slope form to find the equation very easily. But first you need to find the slope. Well, slope, remember, is y sub 2 minus y sub 1 over x sub 2 minus x sub 1. So in this case, I'm going to pick this to be x sub 2, y sub 2, and this to be x sub 1, y sub 1. So that's going to be negative 1 minus negative 3. Be careful with that. Over 5 minus 4. So that's plus. So 3 minus 1 is 2. So it's 2 over 1. So my slope is 2. Now, to put it in point-slope form, I just pick one of the points. I'm going to pick the first one. So y minus negative 3 equals 2 times x minus 4. I'm just plugging in this equation right here. Okay? So that's y plus 3 equals 2x minus 4. Now that is point-slope form. If I want to put it into slope-intercept form, I simply distribute, then subtract 3, and I get 2x minus 11. So this is slope-intercept, this is point-slope. You'll have some problems with those. Now, Hoy and Vux. Let's talk a little bit about, just review horizontal and vertical lines. Remember, horizontal lines, the reason you want to memorize Hoy and Vux is this. Hoy means horizontal, 0 slope. It's a y equal equation. Vertical is undefined slope, and it's an x equal equation. So if I drew this and said that this point right here is negative 5, it's horizontal, and it's a y equal equation, y equal negative 5, slope of 0, because you can walk on the floor. The floor is 0. But if I take and I make a vertical line, say that's at 4, x equal 4 then, because that is a vertical line, it has undefined slope. So that's an x equal equation. So if you have any questions with that, hopefully Hoy and Vux help. Also with lines, parallel and perpendicular. You remember from geometry last year, parallel means two coplanar lines that do not intersect. Parallel means two lines that intersect in a right angle. Well, when it comes to lines and linear equations, they're parallel if they have the same slope. They're perpendicular if they have what we call opposite reciprocal slopes. So if I gave you a slope of 4/3, the parallel slope would be 4/3. The perpendicular slope would be negative 3/4. So it's just the opposite. So if I have a slope of -1/9, what's the parallel slope? -1/9. What's the perpendicular slope? 9. Okay? Now the last concept in chapter 1 is correlation. And we really are talking about correlation as it refers to a line of best fit and a regression calculator, the correlation coefficient. We call it R, and it's on our calculators. And I'm going to try to show you this in person or via Zoom. And basically it says that the more positive correlation, it gets closer to 1. 1 is a perfect correlation. The more negative it is, like the graph is negative, as it gets closer to -1, it's a perfect negative correlation. But if you get close to 0, there is no correlation between the equation and the points. Meaning, if you look at this picture, you can easily tell what I mean by that. Letter A is a perfectly correlated line in the negative direction, so it's -1. Letter F is perfectly correlated in the positive direction, so the correlation coefficient of R is 1. But the rest of them, you can see, barely any of them have a linear correlation. I can't hardly make a line out of B. That's why the correlation coefficient is so low. C is 0. There is no correlation. Same with D. E, we can kind of get a line of best fit. So it's 0.2. This is -0.3. Not real good. C and D, obviously, there's no correlation. Okay? So we'll have to use our calculator to calculate those. Then we get the assignment, and please work on those. You're going to have a couple days to work on those and get those completed before we start our real stuff when it comes to Chapter 2. Also, please be practicing the AccuPlacer if you plan on taking this for college credit.